Good morning, my name is Teo Rocco. I'm a senior aerospace engineering student, and this is my engineering honors capstone project, which I completed with Professor Was and one of his PhD students this past year. My project is on finite element modeling of mixed mode delamination propagation in Abaqus explicit with nonlinear cohesive softening laws. Composite materials are increasingly widely used in the aerospace and automotive industries, especially for their high strength to weight ratio and their ability to be customized to fit a specific application. However, one of the barriers to their adoption is that modeling of the failure of composite materials is quite difficult. And as you can see in figure 1 here, they can fail in many, many ways, each of which has to be modeled separately. So we have interlaminar failure modes, like in D here, where the two layers of material peel apart. And we have intralaminar modes, where we have fiber kinking, fiber rupture, and matrix failure. The focus of this project is specifically on delamination, which we can model in using finite element analysis, as long as we have special treatment of the interface between those two plies. So one of the methods to do this is with the cohesive zone model, where we actually add a discrete layer of elements between the two plies, and we call that our cohesive layer, and that layer models the adhesive, in a sense, between the plies. These are nonlinear finite elements, and on each element we assign a traction separation law, so-called cohesive law, which dictates how the elements fail. The cohesive law is usually linear until some critical value is reached, and then we have a softening law, a softening curve afterwards. And over here, on figure 3 on the bottom here, you can see some of these laws, and you can see the linear increase and then the softening law, which can be linear, as in this case here, or it can be some arbitrary nonlinear shape. Especially, it can even be discontinuous if you have something like discontinuities in the material. These cohesive laws can be determined by experiments, and in fact, if you're only using a triangular law with a linear softening portion, you only need a few variables to define them. However, they're usually only quantified for pure mode loading, so mode 1, and then mode 2, mode 3. But real-world conditions aren't necessarily pure mode. So we define mixed mode laws, which allow us to empirically relate the pure mode cohesive laws to a mixed mode application. And these are usually done by fitting empirical relations to experimental data. And the two most common ones are the power law and the BK criterion, which are defined here. Experimentally and in models, we can load specimens in pure mode 1 and pure mode 2 using the DCB and ENF tests. And then we can load them in some sort of combination of mode 1 and mode 2 using the mixed mode bending tests. Now, the objectives of this experiment are to build several models in those DCB, ENF, and MMB configurations, which let us study an implementation of the cohesive zone model across a range of mixity ratios, and then use those models to test the novel mixed mode formulation and to see what the effect of the shape of the cohesive law has on the results. So we did this. We built a series of 5 finite element models and using DCB, ENF, and MMB tests over a range of mixity ratios. In the MMB cases, we actually discretely modeled a loading arm here, which we use to load the specimen in a non-pure mode loading conditions. These models were actually built based on geometries and material properties from a paper by Kruger in 2015, which we're using as a benchmark result to compare our data to. These models performed well. The deformation we see here in this figure is consistent with deformation we see in experiments. And furthermore, if we look over here, we can see that the delamination front is also consistent with what we see in experiments. So this figure shows just the cohesive layer at various points during the simulation, and the areas where elements are missing are where they've failed and been deleted. And we can see that that delamination front, as it propagates through the cohesive layer, is curved, which matches the curved delamination front that we see in experiments. In terms of the cohesive law, we developed a method to generalize it using only a few parameters, using a Bezier curve for mode 1 and then another one for mode 2 to define the softening portion of the law. We made some assumptions based on experiments from literature to constrain these values to decrease the parameter space that we were testing. And then we tested 4 curves for mode 1 and 4 curves for mode 2, which you can see here. And then we tested each combination to try to find the best set of RA and RB parameters that would give us results that most matched the benchmark values. So here you can see our results in figure 5. This is a load displacement curve for the whole specimen. And we have the results with our best set of parameters, which we found to be RA is 0.23 and RB is 0.9, overlaid with results from the power law and the BK criterion. Our novel formulation doesn't perform perfectly. It certainly overshoots at high mixed data ratios and undershoots at low mixed data ratios. However, the performance is pretty on par with that of the power law, and almost as good as that of the BK criterion across the whole range of mixed data ratios. In the future, we would like to expand the parameter space for the RB and RA parameters to hopefully be able to determine an empirical relationship between the parameters and the peak load that is reached on the load displacement curve, which we hope to be able to use to tune the shape of the the shape of the pure mode cohesive laws using simulations. Thank you so much for listening to my presentation. If you have any questions, I would be happy to answer them.